Hey everyone, coming to you today to talk about some of the material that was in Lab 5. Of course, you're not required to do Lab 5, but I thought that I would go over some of those materials so that you'd have some sense of some of the analyses that you need to do for your homework. Before I do that, I just want to show you how glamorous it is here in my house with my setup. You can see me here. This is what I'm speaking to you from. My standing desk on top of the washing machine and a cooler. So let's get to the lab. In Lab 5, we did a few things focused on kind of getting a start on using categorical variables in regression. The first problem is a problem which is really just there to show you that ANOVA and regression do the same thing. They're equivalent techniques when we are using categorical variables. If you only have categorical predictor variables, there's really no sense in doing it as regression. It's just more work, but we'll see how the two are equivalent. So for the first problem, it's really just running the two analyses, showing how they work together. So the first one is the training and stress example that we may have seen before. It's got two factors. One is training, a dichotomous variable with categories of yes and no, and the other is stress, which is a continuously, and the other is stress, which has four levels, and then we have a number of errors, which is the dependent variable, and that is continuously scaled. So just running it as a straight up ANOVA, you can see that we have no effect for training. There is an effect for stress, and there is an interaction effect. So there we would need to go in and tease out what those effects were, as we did in the handout, so I won't talk more about that. But one thing we can see is ANOVA is really set up for this sort of analysis. It just knocks it out in one go. I ran this using a series of steps in regression. I ran 3 models just to show it hierarchically. You can just we'll just take a look at the final model, as that's the one that's got the real action in it. So in the final model, one thing that we see is for every variable that is categorical, it's now broken into new variables that reflect the number of categories minus 1. So training is now coded into a variable called training yes. This just means that people with yes are being compared to people who said no. Stress low, stress medium, stress no, a little bit challenging to figure out what those mean. Those are all being individually compared to the group that was left out, which was high stress, which is coded as the comparison group. And then the interactions, we get an interaction term, which is basically multiplying every level of every new variable within a specific factor by the other. So training gets multiplied by all 3 of the stress variables. Those coefficients there, they're really not any use in terms of interpretation. We would need to do graphs and things to interpret them. But that's what you get in regression. The results aren't particularly clean. But we'll go down to the final model here. When you ask for the ANOVA statistics from this regression model in the final piece, you'll see that it gives it to you, and it looks exactly like what we got with ANOVA. The big piece there is that ANOVA and regression are both doing exactly the same thing. They're both just ANOVA is basically just a version of regression that has shortcuts and is made easier by the fact that you're only dealing with categories rather than a continuously scaled predictor. Big point here is anything we can do in ANOVA, we can do in regression. If you just have categorical variables like in this problem, it's easier just to do it with ANOVA. You get the same results, and it's a lot simpler. All right, so moving on to the more important applications here. More importantly, we're going to be focusing on using a combination of categorical and continuous predictors. And that's really the point of this this entire assignment, is to get at how we can do that and some of the challenges behind using categorical and continuous predictors. In particular, some of the challenges behind getting at interactions between those variables, between categorical and continuous variables, and then later interactions between continuous variables. Here I'm asking you to predict errors from stress and the variable called experience, and then provide a graph that summarizes the interaction. One thing I want to note here is we need to center the continuously scaled variable. And one of the things that is a challenge in doing that is a quirk of the interactions package. In the interactions package, it will give you an error when you do plots if you haven't done something very specific and very picky in the way that you center your variable. You can see here I've got lab 5A experience, that's my underscore C. That's going to be the centered version of my variable. I'm centering that variable, and I've got it as numeric. I have got, and I'm centering it, and the kind of new piece here is you have to specify it's a numeric variable that you want, and then I'm scaling the old variable using the scale command, which is a centering command. Scale equals false means don't standardize the variable. That as numeric piece, if that's not there, you will get an error in your plot. It's very strange why it does that. Just centering it regularly does produce a numeric variable, but there's some attributes to the variable that are causing problems from the interactions package. There's a lot of people who have commented on the interactions package about how that's an issue, but they don't seem, the author of the package doesn't seem to think it's a big issue because it can be fixed in this way. Here I ran 3 hierarchical models. The first one, it includes just stress. Then I add experience, and then I add stress times experience. And you can see the ANOVA statistics that we get there. I'll just focus on the final model because that's the one that has the most interest to us. And actually getting your output in terms of these ANOVA statistics rather than the t-values is probably a little bit easier when we're doing this sort of analysis. We saw that stress got broken down into 3 variables. Each of them had their own t-value. Those are not particularly useful for what we want here. In particular, in this case, we're really most interested in the interaction effect. And having 3 t-values representing the different aspects of the interaction is not particularly useful. So here we've got stress and experience and their interaction. The big piece of interest here is that, all 3 are significant, but the big piece of interest here is that the interaction is significant. So we're going to focus on what that interaction looks like. The strategy for breaking down interactions is an analysis called a simple slopes analysis. Those of you who took an ANOVA course or my ANOVA course might recall that we break down interactions in ANOVA with what are called simple effects tests. These are basically the same thing, but they're working they're working in a way that's appropriate for situations when we have a continuous variable in the interaction. You can see the code here. This comes from the package interactions, which is for the most part pretty good for our purposes. And what it's going to do to break down that interaction, because just saying that there's an interaction doesn't tell us what's happening, is it's going to break the interaction down by a moderator. Here, the moderator that I chose is the categorical variable. If you're dealing with a categorical variable and a continuous variable in an interaction, using that mod x command, I would always apply it to the categorical variable. We'll see what we get here. We'll see that that's not always possible. The predictor variable is experience, and what that means is that we're going to look at the relationship between experience and errors broken down by the different levels of stress. So the first piece that we get in our simple slopes analysis is when stress equals no, people in the no stress condition. Here's the relationship between experience and number of errors, and we can see that that's not significant. One thing that's a little bit confusing in this output is you get an intercept. Don't worry about the intercept. That's just asking whether the mean number of errors deviates from 0, which isn't really an interesting question in this context. So slope of experience when stress equals no is not significant. Now, if we had no interaction, we would expect basically the same thing across each of these levels of stress. For no stress, low stress, medium stress, and high stress, we would expect, if there were no interaction, for there to be the same relationship between experience and errors. They could be significant in all of them, they could be non-significant in all of them, but we would expect roughly the same slope. When we do have an interaction, we're expecting different slopes at the different levels of stress, or at least one of those levels will be different than the others. We can see for medium stress, and the ordering here is a little bit odd, but we can see here for medium stress, we also have a non-significant relationship. For low stress, similarly a non-significant relationship. When we get to high stress, that seems to be where the interaction is being generated. Remember, the interaction means that the relationship between the predictor and the dependent variable is different across the levels, or across at least one level of the categorical predictor, or what's called the moderator in this case. We can see when stress is high, experience is related to fewer errors. And I get that from the significant result, the P of 0.007, and the estimate, negative 0.46. So we know there's a negative relationship between experience and errors under conditions of high stress, suggesting that, or at least for the people in this study, that experience led people to be able to work better under high stress conditions. Now, a few things to note about these simple slopes that we get. By convention, these are always unstandardized, and for now you can just report them as unstandardized. I kind of don't like that, but there are ways to get standardized slopes here, but I don't want to, but we probably don't need to bring that in and add extra complexity. So you can just report the unstandardized one. I would continue to report the standardized slopes for the regular analysis though. And here's a graph. Oh, I'm sorry, let me go over the code here. So the interact plot is probably looking at it much easier way to make graphs for interactions. I gave you some information on how to do it in ggplot. I still like that approach because I feel it's more flexible and you can get eventually a better graph. But interact plot is probably going to be easiest for our purposes, as we're not publishing this stuff. We just want to have a graph that helps us to interpret the relationships. So you can see interact plot has pretty much the same code as we had for simple slopes, but what I've added here is a confidence interval. That confidence interval is going to be shown graphically, which is nice. And then I just have labels, and I see I've got one wrong label here, which is education. That should I'll fix that and upload a clean version that should read experience on the bottom, and it should read stress on the side. But we can see for the different stress conditions, a high stress and medium stress have kind of negative relationships, although we saw that high stress was the only one that had a significant relationship. And then we see with no stress and low stress, there are positive slopes. However, those are non-significant, so we don't need to worry about them. So big interpretation there. Experience matters as stress rises. Experience becomes more important, and it becomes significant finally when we hit the high stress conditions. I'm sorry, I need 1 second here. All right, folks, I am back. Through the magic of technology, I have updated that graph just to have the correct labels. You can see what those are, and this file again will be available for you on Canvas. Just to go back to this piece, in case people didn't miss it, because it did take me a little bit of time to figure out. I want just to make clear that you may get an error that looks like this. Experience C was fitted with type N matrix, but type numeric was supplied. As usual with R, these error messages are like crystal clear and never leave any, not confusing at all. This is what that as numeric piece in the code that I provided gets around. So definitely be sure that you are using that sort of approach, or the approach that I outlined in this handout. Otherwise, you will get that error, and it's really frustrating, and it doesn't really tell you anything. All right, question 3 was an ANCOVA. Use ANCOVA to predict errors from stress with the covariate experience. Here we're going to ignore training. What does this tell you about the impact of each variable? First part was just testing the assumptions. Remember, the ANCOVA assumption is what's called homogeneity of covariance or homogeneity of regression. The gist of that is that the relationship between the covariate and what we call the factor, whatever the categorical variable is, doesn't affect the relationship between the dependent variable and the covariate is the same across each of the levels of the factor. And what that means is that we don't have an interaction. So it's easy to test this assumption simply by running regression with an interaction term. So we've got stress and experience. We're again using this in ANCOVA form. And we can see there is an interaction, so ANCOVA would not be justified here. So if somebody wanted to use this in an ANCOVA, the reason why people often do ANCOVA is they want to ask questions like, does this factor predict variability over and above this other variable that we know should be related to the outcome? That wouldn't be an appropriate question here because it violates that assumption. All right, question 4. This one looks a lot like a question on the homework. However, the results are different because this is a different data file which produces a different pattern of results, but it's basically very similar to one of the problems on the homework. So we're going to predict occupational prestige from 2 variables, person's level of education and their mother's education. Can see we've centered both of I've centered both of these variables, again using that as numeric piece. And then I simply ran a regression with both of the variables in there. If the code here, if you simply multiply one variable by another, it gives you the individual effects and also the interaction effects. It's a shortcut way to write this. And see the output here, and one of the nice things about interactions with continuously scaled variables is that those continuously scaled variables, they are going to produce a single coefficient because they're not being broken down into groups. You only need one variable to represent the continuously scaled variables. We can see mother's education is significant. However, it's got a negative slope, indicating that there's a negative relationship between mother's education and occupational prestige. We can see there's a positive slope for education, suggesting more education, more occupational prestige, and then there's an interaction, which is really what we're here for. You get this error sometimes when we run LM beta. This is from the quant psych package. I would just ignore it. I don't think that there's anything here that makes any. There's nothing here that's wrong with these data. I think quant psych just has a strange warning piece. And see mother's education here, negative relation, negative slope, education positive, and then the interaction, the direction of that slope is not interesting. We would still report that, or report that standardized coefficient, but it's not really telling us anything interpretable. So the big piece here is we know, okay, mother's education is negatively related, education is positively related, but what about the interaction? The interaction is going to be harder to interpret. We can't just look at a coefficient to do that, and that's why we break down the interactions. Now, in terms of breaking down these interactions, we're going to be looking at the effect of one variable across levels of another variable. However, we don't actually have levels. We don't have a categorical variable here. So what I've done is I've assigned education as the predictor. That means we're going to be looking at the relationship between education and occupational prestige. And I've made mother's education the moderator variable. What that means is that we're going to artificially create 3 levels of mother's education. And the most common way that we'll do this is we'll get a slope for mother's education scores that are 1 standard deviation below the mean mother's education, so low education. We'll get them for being right at the mean of mother's education, and then we'll get them for 1 standard deviation above the mean in mother's education. And you can think about this really broadly as low, medium, and high groups. Below average, average, and above average. Lots of different ways to think of it, but what we're doing is we're creating artificial categories here, just so that we can get a look at what's happening across different levels of mother's education. All of the mathy type stuff I showed you, where we can calculate this stuff by hand, that unfortunately, well, that fortunately for you, goes away when we have a tool like this that can calculate that for us. It used to be you'd have to calculate those slopes yourself, and that made this process a lot harder. So you can see the first analysis, simple slopes, when mother's education is -1 standard deviation, that's the 1 standard deviation below the mean. You can see the slope there is positive and it's significant. So there's a positive relationship between your education and your occupational prestige at lower levels of mother's education. Remember that these are unstandardized coefficients. That's why this value is over 1. Then we go to an average amount of mother's education at the mean. We can see that there's still a significant relationship, but one thing to observe here is that the size of that relationship is about half, or less than half, of what we had for the low education. So as we go up, as we have greater mother's education, your own education appears to be less related to occupational prestige. And then as we get to the top, we see that we now have a non-significant relationship. So for 1 standard deviation above the mean on mom's education, there's no relationship between your education and your occupational prestige. And then the interact plot, can see here somewhere. There we go. So we've got mom's education being broken down, and then we have your own education. And you can see that that positive relationship between your education and prestige is strongest for the -1 standard deviation. It's still significant but weaker for the mean, and then it's practically flat for 1 standard deviation. That was that non-significant relationship. All right, in terms of writing this stuff up in APA style, here's a nice example. You want to get the R² and its associated F value out of the way first. More education relates to greater occupational prestige. I want to talk about each of the coefficients. So first, more education related to greater occupational prestige, higher levels of maternal education related to lower levels of occupational prestige, strangely. Then I usually say something like, these effects are qualified by a significant interaction, give those the terms for the interaction, and then information from the simple slopes analysis. Breaking the interaction down, relationship is strongest for lower maternal education, weakens for average maternal education, and becomes non-significant for high maternal education. So definitely, the homework assignment, use this as a template for how you will put together your presentation. Note that we've got B stars being the standardized coefficient and B values being the unstandardized. And that just reflects the convention within the field to use the unstandardized coefficients for the simple slopes analysis. I don't know why that's convention, but I really see everybody presenting it that way, and even some folks saying that that's the preferred approach. It doesn't make a big deal of difference here. All right, that's all I got for you. Hope everybody stays well and is progressing on the homework assignment.